Continuing with gravitational fields, we're going to look at orbits and satellites. So one key thing is going to be Newton's gravitational law, something we've looked at before. So we're going to utilize this. But also, because a satellite is essentially going around in its orbit in a circle. Now, often things do orbit in elliptical orbits, however you can actually get a near circular orbit, but we'll definitely be suggesting that they're going around in circles for simplicity. So here's my satellite, little m, big M is the mass of my planet, and the force between these objects, obviously the force on M and big M are equal in size, and it's moving with velocity v. This is a constant change in direction, so its velocity is changing, it's moving in a circle. This is circular motion. So one thing we will briefly discuss is circular motion. That's in a separate video, but for now we're going to use the fact that this centripetal force that causes this to move in a circle, the centripetal acceleration is v squared, that's the velocity of the object squared, divided by the radius of this orbit, r. And obviously centripetal acceleration, Newton's second law, mass times acceleration. Okay, so this is the centripetal acceleration that causes that motion. Now, that force then is the force due to the gravitational pull between these two masses. So what we can say is, we could say that the size of this force is the centripetal force. So this equals this. So m, little m, that's the mass of the satellite, v squared over r equals g, big M, little m, over r squared. And I can neaten this up. Let's put this in terms of the velocity. So if I bring r up, basically cancel the masses either side. So what this says is that the velocity of your object has nothing to do with the mass of your object, only really to do with the size of the planet and how far away it is. But we'll see this now if I rearrange this. So if I bring r up, still over r squared, and well, I'll square root that after this. So I'm going to cancel these r's and then square root both sides. So the velocity of my satellite, gm over r square root. So what we're suggesting then is the velocity is directly proportional to the mass of the planet, the square root of the mass of the planet. So if your planet is larger, for the same radius orbit, you're going to be traveling at a much quicker velocity. And also the velocity is inversely proportional to the square root of the distance r from the center of the planet to the satellite. And one thing to note there is the further away you go, then the slower you'll be traveling. The bigger this number becomes, the smaller this number becomes. Now, going back to thinking about things moving in a circle, what we can suggest is this will move around and cover the distance, the circumference of this circle. So the velocity of the object would be the distance travelled, so around once, and the time taken to do that we'll call the time period. So we can actually now look at velocity and time period. If you can see here, the time period is inversely proportional to the velocity. So not only if you are further away from the planet, travelling slower, then if this number goes down, this number goes up, so it takes longer to orbit. So the further away a satellite is, the longer it takes to go around the planet. Right, just thinking now, what I'll do is I will, this is a nice key equation. However, we can put this in terms of the time period. So basically, if I can substitute the velocity 2 pi r over t here, I can actually get an expression in terms of t and r. So I'll do that now. So I'll bring this back to where it was v squared equals gm over r. And now I'm going to replace v with 2 pi r over t. So 2 pi r over t, that's all squared, equals gm over r. And if I expand this out and then I rearrange for t, so I've got 4 pi squared r squared over t squared equals gm over r. If I rearrange for t squared, I'll have t squared is equal to 4 pi squared, 4 pi squared r cubed over gm. Okay, and that's a nice expression as well. The 4 pi squared over gm is a constant for the planet, because that m's not going to change. G, the gravitational constant, is not going to change. 4 and pi squared is not going to change. So what we're suggesting is that t squared is proportional to r cubed. Okay. Now we'll discuss this in a bit more detail when we talk about some laws, Kepler's laws. And this is his third law, so we'll talk about that in a bit more detail when I describe his other laws. But so far, what we've discussed is that you can work out how fast something should be travelling around a planet depending on how far away from the planet is. And now what we've found is we can actually work out how long it takes to go around that planet depending upon how far away it is from the planet. Let's turn this over. Okay, so let's talk about some types of orbits. And what I'll do is I'll supplement this with some questions that I'll answer in other videos. So in those videos, we'll do a question on low Earth orbits, medium Earth orbits, and then something called geosynchronous. And also I'll talk about what the difference is for geostationary orbits. Okay, firstly, low Earth orbits. So these orbits are typically about 300 kilometers to 300 to about 2,000 kilometers. Okay, so that's how far away the satellite is to be classed as a low Earth orbit. A good example, and an example that will come up in exam style questions, is the International Space Station. Okay, so there'll be a question on that. Medium Earth orbits, they're typically around 2,000 kilometers up to about 35,000 kilometers. And these type of satellites are often, a good example would be a GPS global positioning system. So they're the satellites that make sure that you can drive to a certain location somewhere around here. Now, anything at this distance will have a certain time period to it, and anything in this range will have a certain time period to it. And then finally, your geosynchronous, geostationary. Well, synchronous means that it's orbiting at the same time period as the Earth. So in other words, its time period is 24 hours. Okay, and we can calculate how far out it should be. Now, the only difference between a geosynchronous and a geostationary, they both have a time period of 24 hours. It's just that with a geosynchronous, it's just orbiting around at some inclination. It could be going around here, around here. It takes 24 hours. What it means is that at some point in the day, it will be at the same position every 24 hours, but it won't remain at that position above the Earth. That's a geostationary orbit. That's where it travels directly around the equator, and it's always constantly above that point. As the Earth rotates, the satellite will rotate with it. Okay, so both geosynchronous and geostationary have a 24-hour time period, but the geosynchronous, which is at an incline, will just be at a certain point above the Earth at the same point each day, whereas a geostationary will always be above that point. Okay, so it can just track that position, but it has to be orbiting around the equator. So I suppose typically then you've got 24-hour periods for your geosynchronous and then you'll have about 12 hours for a GPS satellite, and then the International Space Station, in the question that we'll do, it has an orbital time period of 92 minutes. Okay, so approximately goes around 16 times a day. Right, so I think for theory we'll end there, and then I will do some exam style questions in other videos.